Hi, and welcome to this introductory video on the topic of electricity. This is a topic that strikes fear into students from year 7 right the way up to year 13. But hopefully by the end of this series of videos, you'll be able to go out into the world with a smile on your face and a spark in your step. Let's start by looking at electrical charge and current. We know from the circuit symbols video that a cell is something that pushes current round a circuit. Now, one of the simplest circuits we can build looks a little something like this. The current which comes out of one end of the cell flows round the wires, through the bulb, round some more wire, and then back into the other end of the cell. Now, this current we're talking about is actually made up of moving electrical charges. Because these charges can't be used up, this means that the total current leaving the cell must be equal to the total current returning to it. As a matter of fact, in a circuit like this, the current is exactly the same everywhere. So we could put an ammeter here, or anywhere else in the circuit for that matter, and it would always show exactly the same value. One of the best ways to think about this is to think of a river making its way downstream. The current of the river is made up of moving water particles, just as an electrical current is made up of moving charge. Even though the river might bend a little this way and that way, the amount of water that went into it at one end is going to be equal to the amount of water that leaves it at the other, and the current won't change as you go downstream. Okay, now that we're done with our little trip down the river, let's look at electricity again. Now, the equation linking charge and current is as shown. Q here stands for charge, which is measured in coulombs. Capital C for the unit. I stands for current, which is measured in amperes or just amps for short, capital A. And T stands for time in seconds. Now, if you find it useful, here is the formula triangle for this equation. Alright, so let's start off with a nice simple example. Just have a quick read through here and take a look at the diagram on the right hand side. Now, before we do anything with the equation, let's just highlight the key numbers that are given to us in the question. The current is 2 amps and it's flowing through our bulb for 3 minutes. Right, let's get going on the actual solution now. Just writing down the values which we have so far. I for current has a value of 2 amps. Now, for the time, it's slightly more complicated because, as you can see from the above equation, the time has to be in seconds, but it's not a big deal to convert 3 minutes into seconds. So we'll just multiply 3 times 60 to give 180 seconds. Now that we've done that, we can use either the equation or the formula triangle. Writing down Q equals I times T, substituting in our numbers 2 times 180, and we're left with our final answer of 360 coulombs. Right, having done that one, let's go on to a slightly more complicated example next. Just spend a brief moment reading through the question. Now, as you can see, it's looking for us to calculate the reading on the ammeter, in other words, the current in the circuit. The values that we're given are that the charge is 5 kilocoulombs and the time taken is 2 minutes. So let's get cracking. This question is one that could cause a lot of students stress initially. The main reason being that little kc at the very start. Now think back to anything else, which looks a little bit like that. How's about kilometers? So 5 kilometers, we all know, is just a distance of 5,000 meters. What that means is that a charge of 5 kilocoulombs is a charge of 5,000 coulombs. We haven't gotten over that little hurdle. All that remains to be done now is to actually use the equation to calculate current. Like the previous example, the time is given in minutes, but we want to convert that into seconds. So 2 times 60 gives 120 seconds. And now, using either this equation or the formula triangle from the previous page, we make I the subject, so current I equals Q divided by T, which equals 5,000 coulombs divided by 120 seconds, which gives 41.7 amps for the current. Now that you're all experts in charge and current, let's go on to look at potential difference. A hardcore physicist might say something along the lines of this. Although that sounds absolutely terrible, what it's trying to say is actually quite simple, so let's break it down. What's going to happen in this circuit? The answer, of course, is not a lot, as there's nothing present which can push current around the circuit. Going back to our nice cozy circuit from earlier, we have a source of PD in the form of a cell which can push current around the circuit and through the bulb to light it. So what is this mysterious magical stuff known as potential difference? To answer that question, let's go back to a river analogy, only this time we're going to be looking at the river side on and not top down. When a water particle is at the top of the river, it has a maximum amount of gravitational potential energy. As it moves downhill, its GPE decreases and its kinetic energy increases. In other words, the change in its potential energy between the top and bottom, or its potential difference, is what caused its kinetic energy to increase. In the same way, when a charge leaves the cell in an electric circuit, it has a maximum amount of electric potential energy, or EPE for short. As it travels through the circuit and flows through different components, its EPE will decrease, and the energy it loses will be given to components in the circuit. Let's go back now for a moment to our trusty old cell bulb circuit. To see exactly how this works, when our charge leaves the cell here, it has a maximum amount of EPE. When it gets to the bulb, it gives its EPE to the bulb. Because the bulb has been given this energy, it's going to start to heat up, and eventually, when it's hot enough, i.e. when these little charges have given it enough energy, it will start to glow red and then white hot, emitting its own light. Now that we know what potential difference and current are, let's have a look at how these two important quantities are related by something called electrical resistance. Now this is the equation linking V, I and R. V here stands for the potential difference between 2 points in a circuit. It's measured in volts, capital V. I, as we already know, is the current flowing through that point in the circuit, which is measured in amps, symbol A. And as you might have guessed, R is the electrical resistance. It has units of ohms, Greek symbol omega, they're used to represent those. Now just in case you find it useful, here is the formula triangle for this equation. Right, we're going to look at two examples of using V equals IR in this video. Here's the first one. As per last time, let's start by picking out the key figures from the question. As you can see, the circuit is composed of two 1.5 volt cells, an ammeter and a fixed resistor. The ammeter reading, in other words the current, is 0.5 amps, and we've been asked to calculate the resistance of the resistor. So let's get to work. Okay, the potential difference across the resistor in this question is going to be 2 times 1.5 volts, in other words 3 volts. We have two cells there. And the current reading is 0.5 amps. Right, having done all that, we're looking for the resistance now. So all we need to do is use V equals IR. Therefore R equals V divided by I, which equals 3 divided by 0.5, which equals 6 ohms. Easy peasy. Let's go on to a slightly trickier question next. Alright, on to example 2. As you can see, this time we need to calculate the potential difference across the variable resistor in this circuit. Here is our variable resistor, which has a value of 10 kiloohms or 10,000 ohms as we know. And the current through it and around the rest of the circuit is 4 amps. So it's just a matter of substituting those simple values into V equals IR. So let's go ahead. So V is equal to 4 times 10,000, which gives 40,000 volts. or 40 kilovolts if you want to get fancy. Right, let's look on to part B. Now in this part of the question we can see that the student has doubled the resistance of the variable resistor. The important thing to realise is that the answer which we had for the previous part of the question, 40,000 volts, was as a matter of fact equal to the battery voltage, or the PD, across the battery. So we'll just write that into our circuit diagram. Now as we said, the resistance doubled, so it went up to 20 kilo ohms. The current is what we actually need to work out. Now rearranging V equals IR, or using your formula triangle, you can see that I, the current, is equal to V divided by R, just substituting in our values. That gives 40,000 divided by 20,000, which is equal to 2 amps. Now this answer of 2 amps illustrates a really important fact about current and resistance, and that's as follows. In part A, when the resistance was 10 kilo ohms, the current was 4 amps. But in part B, when we doubled the resistance to 20 kilo ohms, the current went down to 2 amps. In other words, this act of doubling the resistance caused the current to halve. Now there's a special mathematical term we use for this relationship. We say that current and resistance are inversely proportional to one another. In other words, as you increase the resistance of part of a circuit, you decrease the current through it. In this example, we doubled the resistance of the circuit, so that halved the current through it. Trebling the resistance would have decreased the current by a factor of 3, and so on. Okay, so that's it. You're done with your introduction to electricity. I do hope it's been useful. Thanks for listening, and good luck with the rest of the topic.